Hello, everyone. Thank you for being here today again. Sorry for the technical issues. Um, we have the pleasure of having with us here today Professor Daniel. He's going to talk about dimensionality reduction, machine learning, graph drawing. So the word is you. Thank you.
Hello, how's everybody doing today? Good. I noticed that the schedule is we have a couple of practical talks. We had Sarah yesterday. Sarah's attending my talk today. You making me nervous. And then this afternoon you have a talk on user experimentation, correct? So it's really good to have a very practical PD summer school. So as mentioned, my name is Daniel Archambault. I'm from the visualization community. I ended up doing some machine learning stuff way back in 2010. I was a struggling postdoc. And what happened was on my second postdoc in Ireland, they said, hey, we have this really good information visualization person here. We understand at that time all the InfoViz people left UCD, they went to other places. And they said, you have this funded project with some InfoViz you need to deliver on. I said, okay, I'll do that. But you'll be in a machine learning lab. And I was like, I don't know anything about that. But I managed to pick up a few things. And now at Newcastle, I headed a group that was part scalable computing, part AI and machine learning, and part visualization. But it's really important to note that I'm not a machine learning person. I'm a visualization person that kind of understands the machine learning thing. So I'll be able to give you ideas of the things that I know, but my expertise is actually in visualizations. It's important to keep that in mind. Now, the dimensionality reduction goes further back. It goes back to my PhD, and I'm going to tell you a couple of stories there. All right. One thing when you become a professor, you lose track of time. When you're a PhD student, if you practice presentation for 20 minutes, it takes 15 minutes to cover. When you're a professor, you think you have a 20-minute presentation, it takes 45. So I'm going to keep track of my times here. I realized the last keynote I gave was 36 slides and it took over an hour, and this is 60. So we'll see how this goes. Okay. Graph drawing, AI, machine learning, etc. So everybody's doing machine learning. Yay. Okay. If you have a research agenda, you can get funded by doing machine learning. If you have a tech startup, you go, hey, I'm doing machine learning, they throw money at it, right? Right. Okay. Give talks about it, everybody's eyes light up, and it's amazing machine learning, yay. Well, about 30 years ago that you could do the exact same thing with the internet. Oh my God, how times have changed. Anyways, so everyone's claiming that they're in this space. And I was talking to some of my friends at Newcastle, and they said, are you AI washing this talk? There's no way graph drawing and machine learning have a strong connection. Well, it does. Oh, do we want? Do you need in? You need in?
No, on but it's okay, right?
Yeah, it's perfect. Graph drawing actually does have a pretty strong connection with machine learning. And I'm gonna show exactly where it is, and some of the guys have really didn't believe this. All right. Can we all agree that Jeffrey Hinton's probably a machine learning person? Yeah, I think so. So here's his TCNE paper. This is the first paragraph of the TCNE paper. First word is visualization. My God. And then if you go a little bit down here, you have Batista, 1994. My God, it's the annotated bibliography of graph drawing. On page 1, paragraph 1 of Jeffrey Hinton's C-SNE paper. Why do you do that? Well, we're gonna explore, and so this talk is actually divided into 3 bits, and we're gonna explore that first question of why a graph drawing annotated bibliography in Jeffrey Hinton paper. So we're gonna, okay, good. So we're gonna now discuss why that annotated bibliography on graph drawing is in the first paragraph on the first page of Jeffrey Hinton's C-SNE paper. That's section 1, where we're going to be discussing the strong connection between graph drawing and dimensionality reduction. For section 2, we're going to then discuss this why dimensionality reduction is actually quite important for machine learning. And I'm going to specifically talk how you can use dimensionality reduction to visualize the activity of neural networks. And then the final part, well, because this is a visualization talk, we can't only really talk about visualizations for technological geeks and AI wizards. We also have to talk for a wide range of audiences and technical backgrounds. And so that will be the third part. Between these thirds, what I'll do is I'll take a few minutes for a break. Okay, so you'll have 2 breaks in this talk.
Are you
Yes.
gonna record?
It is recording. Yeah, already done. Hopefully. All right. So what I thought of dimensionality reduction. Hello. Are you going to watch my lecture too?
Of course.
I'm going to be super nervous.
Yeah, you think so, but it needs a projector move, right?
See, the first lecture, you guys say don't come and see my lecture, and then everybody comes and sees my lecture. All right. So I actually almost did dimensionality reduction for my PhD. I was in Tamara's office. She said, "Hey, why don't you do this dimensionality reduction stuff?" She was really into MDS at the time. I said no. And the main reason why I said no is I couldn't see an application for it. This social network stuff, and yeah, I can see that. This dimensionality reduction stuff, not really. So I turned to graph drawing instead, and I did an entire PhD in graph drawing. Little did I know of these connections. So at this year's Euroviz, there was actually a really good paper that illustrates a lot of these connections, and you guys should probably go read it. Citations there. I'm going to go through a couple of the connections. This one goes through like 15. Okay. And I do include a couple of slides from the Euroviz presentation that I asked the authors. But if you're really fascinated about how dimensionality reduction and graph drawing are strongly connected, I'd suggest going to this paper for more details. So let's go back to the 50s or 90s when I was reading some of this stuff. So here is part of a description of classical multidimensional scaling. So in classical multidimensional scaling, what you do is you construct a matrix related to high dimensional distances. So you have points in a high dimensional space. You're going to construct a matrix that corresponds to these high dimensional distances. And then you're going to use the eigenvectors of the matrix to reduce the dimensionality and get a 2-dimensional projection. And you can see it's essentially going to do these matrix operations on the distances in the high dimensional space to get a low dimensional reduction where stuff, if it in the low dimensional space is nearby, it's going to be nearby in the high dimensional space. Okay. So this is an approach called MDS, preserves these distances. And then I read a paper called Kamada-Kawai. Kamada-Kawai is sort of a force-directed algorithm written in the 80s. And there's this part of the sentence here. The basic idea of our algorithms is as follows. We describe the desirable geometric Euclidean distance between two vertices in the drawing as the graph theoretic distance between the corresponding graph. That's interesting. So we have a situation where MDS considers high dimensional points, the points in a high dimensional space. It computes the distance somehow between those points in the high dimensional space. And then it computes a mapping to 2D such that nearby points in the high dimensional space are nearby in the low dimensional space. Kamada-Kawai has a graph that computes the shortest path distance matrix. And it computes positions of points in the plane again, such that 2 points or 2 vertices are nearby if the shortest path distance is small and further apart if the shortest path distance is large. So essentially, they're very, very similar approaches down to scaling factors, where we just took the high dimensional distance matrix and subbed in the shortest path distance. So these two are very similar. I know Brenda's noticed this. So this is from his book chapter on drawing physical analogies. Kamada-Kawai, 1989, avoids the second potential repulsion by using these things. It's interesting to note that the physically inspired objective function UKK is closely related to the MDS objective. So Kamada-Kawai and MDS have a very strong relationship. Barring a few algorithmic details, you just take the shortest path distance matrix and plop in a high dimensional distance. That's it. Okay. Brenda's went on. And this is from one of his later papers in 2017, where he just basically calls things like Furchman-Reingold force-directed methods, and then he calls these methods MDS methods. So he thinks the connection is this strong. Okay. Some other people, this is a algorithm called HDE, the HDE algorithm. And this was interesting because it is kind of related to the MDS stuff obliquely, but I'm not going to explain that here. But it essentially treats the graph directly as a high dimensional data set. So what it does is computing a shortest path distance matrix is expensive, right? So we're going to take around, I don't know, 60 somewhat pivots. The first one's random. And then we're going to compute the shortest path distance between that vertex and everything else. And then we're going to take the vertex that's furthest away in terms of shortest path distances. And we're going to repeat the procedure. And then the furthest away, and repeat the procedure until we hit 50. Okay? So now we have an n by k matrix, which we can turn into a square matrix by multiplying it by its transpose. And when you compute the eigenvectors of this, you can draw it. And it turns out the eigenvectors of this is essentially applying PCA, which is another dimensionality reduction technique. So what you've done here is you've taken the graph, let's say case 50. You embed the graph in a 50-dimensional space. So you have vertices in a 50-dimensional space. And you can keep PCA on it to draw it. So essentially, you've turned the graph into a high-dimensional data set to draw. Okay, so that's interesting as well. This is continuing to happen. Little bit more information on the sparse stress model that I was talking about before. Remember this classical MDS business I was talking about before, where you have this high-dimensional data set that you compute a projection of? On the sparse stress model, what you do is you do a graph drawing version of that with k vertices. And then you do stress or commodic-like things to lay out the graph. So now you can't tell the difference between high-dimensional data or graphs, pretty much, with all of these sorts of things. And well, in the 90s, they were like, so what? In the 90s, when we talked about graph drawing, or some people talked about graph drawing, or you talked about high-dimensional embedding, you use similar language. So this is a paper essentially on visualizing high-dimensional data. They talk about using spring models. They talk about forces. They talk about all of this language that we do in graph drawing. They refer to graph drawing papers. But I think what happened is at the beginning, these algorithms sort of developed together, and then as fields drift apart, they start using different language and stop talking to each other. And this was one of the main points that that they were making in the Euroviz paper this year. So here's the big drawing that they had in the Euroviz paper from classical MDS all the way up to UMAP, which is a state-of-the-art dimensionality reduction technique. And all of the connections of where they use bits and pieces of each other. And here we go. T-C-N-E and Kamada-Kawai are there. So graph drawing and dimensionality reduction do have a well-known strong connection. The easiest way, at least for me, to see this is in the connection between stress-based drawing and MDS. So anything that uses a Kamada-Kawai-like algorithm, that includes all of the stress optimization techniques, have similarities to MDS. But there's stronger connections, and you can see some of those connections by looking at the paper that was published at Euroviz this year. And how does this have any connection with machine learning? Well, if you look at things like T-C-N-E and those sorts of things, they have connections to these dimensionality reduction techniques. They use them as previous work, and ergo do have connections to these stress optimization methods. And so when people in the club ask me, is there a connection between graph drawing and dimensionality reduction machine learning, I can say yes. Jeffrey Hinton's paper actually cites this survey on page 1, and it's because of this strong connection. So, yay. And to my younger self, who said dimensionality reduction was useless, oh, I can't say that now. I apologize. Okay, good. Okay, so that is part one. We can maybe, well, we've already taken lots of breaks because of the thing. I was going to take a small 5-minute break here. Do people want to do that? No? Yes?
I think let's continue.
We just continue? Okay. All right. Did you continue all the way through last time? You did? Okay. Mm. What slide am I on? Am I actually going fast? That's interesting. Okay. All right, so we're going to continue here. So we made the connection between dimensionality reduction and graph drawing. Now there's a question, why on earth would people in machine learning like to look at high dimensional data sets, right? Remember, I was talking about machine learning here. I wasn't talking about dimensionality reduction. Well, I could use the same argument that I used a few seconds ago, and I say, see, Jeffrey Hinton's doing it, ergo it's important to machine learning. But I think that's a pretty flimsy argument. So I tried to look in the T&E paper. In the T&E paper, he says things like it's important in many domains. If you look at these cancer data sets and that sort of thing, there are these points in high dimensional space. He doesn't have a real smoking gun. This is why we want to look at high dimensional data in that paper. But if you try to read between the lines, I think what they're trying to do is they're trying to figure out the separation between the data points in the high dimensional space, to figure out which sorts of learnings or which sorts of transformations of the data space could help you learn better. So I really wish he said something explicit, but he didn't. But I think we can say standard viz arguments, which is, okay, if you want better models, if you look at your data, then you can select more appropriate models or better transforms. Okay. So we talked about visualizing high dimensional data. And this will, what it will allow us to do is will allow us to look at a data set in 50 some odd dimensions down to 2. But what about models? Can we actually use some of these techniques to actually look at how a neuron-based model is functioning? And it turns out we can, and I'm going to present this. When I'm talking about methods for visualizing models in this presentation, unlike some of the dimensionality reduction stuff where I took a broad approach, I'm not going to take a broad approach here. I'm not going to illustrate all of these connections. What I'm going to do is I'm going to focus on a very particular set of techniques. In fact, about 3. It's really important to note that there's many other techniques for visualizing models in the machine learning literature, and I'm going to not talk about them at all. Okay? So I'm giving you a very biased view here, but the main reason why I'm giving you that biased view is for the 3 following reasons. Number 1, I know this stuff a little bit better than the other stuff in machine learning. Remember, I'm a viz person. So I'm going to talk about the stuff that I'm more comfortable with. That's the first thing. The second thing, this shares a stronger connection with the graph drawing approaches. Okay. And I'm going to reiterate that this one here is not comprehensive. And that's sort of important to underline. Okay. People know neurons, neural architectures, that sort of thing, a little bit. I'm going to give you a little bit of some basics here. So generally, when we speak of multi-layer perceptron network or some of the DNNs, the basis is the neuron, which is a simulated neuron. It has a bunch of inputs. So we have X to XN. Those are essentially inputs that are going to come in here. And they have weights. Okay. And if the signal coming in multiplied by those weights is over a threshold, the neuron is going to fire and Y is going to emit a signal. And otherwise it does not. An interesting thing about this, so X1, X2, all the way down to Xn, that can be seen as an n-dimensional space, right? And W, these weights cause it to be a plane in an n-dimensional space. And firing occurs because it's greater than a threshold if the point is above. If it's below the plane, it does not fire. So there's a geometric representation of this as well. Now, if we look at a single hidden layer here, you have these neurons lined up, okay? There's a layer of neurons before and a layer of neurons after, or an output layer. And now you essentially have a series of planes in the high-dimensional space. All aligned up there. Okay. This one is something different. Oh, I forgot to explain that. Shoot. I gotta go back. When we talk about training of neural networks, do people understand a little bit of that? Not much? Some? So you can initially set those weights as random weights, right? And then if the neural network gets things wrong, what you do is you adjust the weights really small. You move this plane towards the point. Really small things. And you keep on doing this over and over on all of your data sets until you achieve good accuracy. You adjust these weights until you get most of your training correct. So, essentially, you'd have a score, and this score is related to something called the loss function, which we're going to talk about in a second. So, loss landscapes. This is probably the furthest away from graph drawing I'm going to go, but I think it's interesting. What these terrains show is for a particular point. So yeah, you're going to do, again, a form of dimensionality reduction. And the elevation of this landscape is how well the network is performing. So really low points on the landscape is good performance. Really high points is bad. And one of the things you notice, let's say we're going to try and optimize this neural network. We're going to try to learn something. If you're on one of these jaggedy landscapes, what's your chance of getting stuck in a local minima for optimizing these weights? High. If you're on a smoother landscape, it's lower, right? So by visualizing these sorts of things, you can understand how easy or hard it is to learn. And I'm gonna try to explain some of this in a second. So what is loss? I kind of explained it previously. I'm going to now go into it in a little bit more detail. So theta is essentially the sets of W's in your networks. It's all of the weights. Okay. And we're going to have M pairs of, so this is the input. So for example, an image. And yi is essentially the label. So that will be cat or dog, actually. And the loss is this function L. And essentially, what you do is you evaluate the network on how it's performing on all of the M labels. This could be as simple as right or wrong, or it could be a more complicated function as to how close you are to the image. I won't go into some of those details, but you can basically think about this as a way of characterizing how well you're doing on these data sets as a floating point number. All right. So how do we create one of these trains? Well, the first thing you're going to do is you're going to train your network to the best performance that it can get. And you have this optimum. So hopefully that's going to be a point that's very low on your terrain. And then what you're going to do is you're going to look at all the W's. That's your theta, all the weights in your network. And you're going to choose two random directions in this really high dimensional space. And what you're going to do is now you have a plane, and you're going to interpolate along those points. So with those two random directions, okay, you're going to essentially for each point in this plane, you're going to be able to sum up the addition of these vectors times a constant. Okay. For each point in this plane, you have a new set of weights, right? You don't need to retrain your network. You have a new set of weights. And what you can do is you can run the test images through that again and get a new loss value, which is a new point on your landscape. Okay. And so once you've sampled this plane, you now have this landscape. What's important to note, and this was quite counterintuitive, if you have a really high dimensional space and you choose two random vectors, there's a high probability of your work falling off. I actually asked one of the grad students to test this a few times, and it's true. So that's actually interesting because that was counterintuitive for me anyways. Okay, so from the loss landscape paper, what you do is you have this star theta, which is essentially all the weights that you've trained in your neural network. And you essentially push the network in small little directions to get sort of like a terrain. Okay. Now, if the terrain is very bumpy, a small change to your weights causes a drastic change to loss. Then that means that if you were to restart the training process, what's the chance of you getting that optimum again? Pretty low. But if it's smooth, a small change in the weights has a small change in the loss. Then what you've learned is a little bit more stable. Okay. Can anybody see a little bit of an issue with computing these loss landscapes? I'm gonna stop talking here. Anybody see one issue? I'm gonna see, anybody wanna try to? Sorry? You do have a problem with growing dimensions. What about growing dimensions in these two vectors? No, you know? What happens if we pick two different random vectors? We could get a very different loss landscape, right? We're talking about really high dimensional spaces here. What's the chance you choose the same vector twice? So this is only one particular view of this high dimensional space, and this has been documented. But you can argue back and forth. You can have a particular view or you can have no view, and machine learning people would like to see something. So that's one of the reasons why this has been a popular approach.
So
Yep.
in this approach, every time you try to plot the loss landscape, you plot the vectors, and every time you get a different landscape.
So let's just put it this way, if the landscape is terrible, then yes. But it fortunately for a lot of these problems, it's not, how shall I put this? The thing you're trying to learn is not that unsafe. Most of the time it kind of works out, but it does have this inherent problem if you have something that's a pathological example. And you know, if there's any theoreticians in the room, you always try to find the worst case example. I'm pretty sure you can find a worst case example there.
But I'm wondering, is this a method trying to improve the gradient descent approach? And what was wrong with the gradient descent? And it's very much like adaptive estimation methods and those methods.
So now we're going back to so when I go back to the TCME paper and I was trying to read why Jeffrey Hinton wanted to visualize data sets. My gut is saying the reason why, and he doesn't say explicitly, which is unfortunate. And I tried to find a quote, but I couldn't. They like to look at these sorts of things to figure out which machine learning approach to apply. With these loss landscapes, essentially, if you have a landscape that's very bumpy, your gradient descent, like easy gradient descent approaches are going to have more difficulty, right? So you might need to choose something that you might need to choose a method that is better at handling lots of local memory, right? You might need to choose something better, right? You're right. I think these sorts of things are about the selection of the method, not necessarily making the method better. Selection of the approach.
Sorry.
Yeah.
So in visualizing the landscape, you only care about the loss? Because if you use images, maybe SNR is more important than loss for us.
Very good question. We're gonna have a few visualizations later that handle that a little bit more directly. And this is, I think, part of the point. Part of the point that I'm gonna make in the third part. So machine learning people are very, very interested in loss. You go to the general public and you say, hey, it has a loss of 4.6. They're like, But hey, it has problems classifying white dogs versus black dogs versus brown dogs or whatever. That might be more pertinent information. In later parts of this, we're going to be talking about ways to visualize which parts of a data set it got correct or got incorrect, as opposed to just a number saying the loss is this. And if you move the weights in this direction, the loss changes this way. So in summary, there are approaches, we're gonna go through some of them that deal with the classifications, misclassifications more directly. Loss was chosen here, why? Because I know people like loss. Does that make sense?
Yes.
Okay. More questions? Okay. So these things actually do show interesting things to machine learning people. So the top row and the bottom row, the top row is a loss landscape of ResNet with skip connections, and the bottom ones without. And as you can see, you have your skip connections, it's much smoother. So when you train the network, your chances of achieving optimum are greater. Whereas if you don't, well, small changes in the weights can produce different changes with different things than what you planned. Ergo, you should probably use your skip connections for training. Cool. Okay. So wouldn't it be great if you could do this? So now, do people know what MNIST is? Yeah, so it's a bunch of handwritten digits. And we have essentially some sort of neural architecture with some random rates. We apply training, and all of a sudden, the digits form into clusters. Well, that's cool. This is visualizing the data more directly. We aren't looking at loss. Each of these individual points is an actual handwritten digit. If two digits are nearby, they are similar in the high dimensional space, and if they're far apart, they're different. But this is drawn based not on the similarity of the images, like in the TSNE paper. This is drawn based on how similar they are in terms of the network. We're going to go through this in a second. Notice I said 2 points nearby are nearby in the high dimensional space. MDS, dimensionality reduction. The first part of this talk is central to this visualization technique. And young me is again kicking himself for saying that this stuff was useless. But anyways. All right, so let's go back to multi-layer perceptrons and that sort of things. So we're going to look at our network again. We have a bunch of hidden layers with neurons in those hidden layers. If we choose a hidden layer for a layer of D neurons, we can look at the activations of those neurons. So think of it as sort of like a Christmas tree, 0 if it's completely off, 1 if it's on, if it's firing. Okay. You can have in between different types of activations. You can look at that as well. That's a point in a D-dimensional space, right? Based on the activations of the neurons. And if you have very similar images, are similar neurons going to be activated? Yes. So when presented with 2 similar activation profiles, if you compute a dimensionality reduced space of this layer of neurons, you'll get 2 points in similar positions to the plane. And if the profiles are very different, they'll be far apart. So this is what you do for each data point. After you've trained your network or at any particular point in the training, it doesn't need to be after you've trained. network, you can use this technique to visualize the training process. What you do is you take all your data, you run it through the network, you look at the layer, you see what the activation profile is, you record that high-dimensional point. Now, for each of your data points, you have sort of like the activations that point causes in the network. And then you compute dimensional error reduction on that, an NDS type thing. And this produces a visualization of what that layer has learned in 2 dimensions. And so here we have essentially, this is SVHN. So it's a set of digits in Street View. We notice that there's 2 clusters of green points in the 2 here. And the main difference, they are both 2s. They are labeled as 2s, but the reason why they're separated, i.e., the reason why the network has learned these 2 things as different activation profiles is one set of the 2s is on a dark background and one set of the 2s is on a light background. Yep.
What's on the left, that's produced by supervision for when you supervise the labels. This way.
Sorry.
So I'm asking, so the ones on the right, one on the left. So what are the data they are representing? Because the one on the left involved supervision of the right. What is the training?
So, okay, the ones on the left, I'm not understanding what you mean by the ones on the left. Do you mean the picture on the left? Do you mean this one versus this one, or this one versus this one?
On the left figure versus not the class. Just in general. So there are 2 figures, right?
Yeah.
One on the right, one on the left.
Yeah.
I was wondering, like just a clarification. So the one on the left is somehow training via supervision.
Oh, no, this isn't. So these are 2 separate training models. In a second, we're going to look at the training process. Okay. Sorry for misleading you there. So we're just looking at trained models here. All right. And let me just see here. The one on the right here is looking at some cases of strange classifications. So you have these points here, which are zoomed in part of this 5s, which are being classified as 1s for some reason. And then up here, you have a 1 that's being classified as a 2, and it's clearly very blurry. So, okay. And here's your training process. So now we take a particular layer. A0 is very close to the beginning with more random weights and that sort of thing. And as training progresses, these points are going to move, right? They're going to drift. Because the activation profiles of similar classes become similar until it's well separated at the end of the epoch. And you can visualize these things by following the trails of the actual points. And you get these tree-like things where the destination is essentially these classes which are well trained and well separated and well understood by the network. So in this case, we aren't visualizing the data itself, we're visualizing the activations of a hidden layer. And as we visualize the activations of this hidden layer, as the network at the beginning cannot separate out the points when it's not trained very well, it's a jumbled mess at the center. And as the network trains and trains and trains, the activation profiles become different. The neurons serve different purposes in terms of classification. And at the end, they're well separated because different classes have different activation. And this is all thanks to dimensionality reduction. Wow. Dimensionality reduction is on the neurons this time, not the data points. Okay. So there's a lot of white space in those diagrams, right? So now what we can do is we can try to reason about some of the pixels between the dots. And the way we can do that is something called a decision boundary map. So in this particular case, for a pixel that has a data point, either based on the actual data or the activations of a hidden layer, we have a point that's projected onto the plane. If that point's blue, we can color that pixel blue, right? If the point is white, we don't know. And essentially what decision boundary maps do is they come up with a way to figure out what is an appropriate color for each of the pixels. And why do we want to do that? Well, now we have sort of a region of the plane that we're pretty sure that a lot of things in that region are going to be zeros. We're pretty sure that a lot of the regions inside the yellow are going to be 8s. One important thing, remember, we're dealing with really high dimensional spaces here. So it's not necessarily the case that these things are connected. Of course, they can be disconnected. You can have many regions corresponding to the same digit in this particular case. And so how do you do this? Well, you just use the technique previous. You can actually use the data as well. Okay. And then we're going to train a second neural network. So we're going to use the dimensionality reduction projection. And we're going to use that as input. So you have your low dimensional point as the input and the corresponding high dimensional point as the label. And we learn a neural network, or we train a neural network that maps the low dimensional points to high dimensional points. Now, some of your people are like, wait a second, Dan. So we took this 500 dimensional space and went down to 2. We threw away a lot of information. Now we're taking a 2-dimensional space and we're going back up to 500. Where are we getting this information from? Okay, don't worry. Essentially, what you're doing when you do this is the screen's now sort of a sheet. And essentially, you're taking the sheet and sort of contorting it in the high dimensional space. So it's sort of following the data in the high dimensional space as a 2-dimensional thing. But once you train this network, what you can do is you can march through the pixels. And as you march through the pixels, you can predict where it is in the high dimensional space. And then you take that point in the high dimensional space, you run it through your neural network, and you get an answer for classification. Now,
So in
yes.
this second network, you take the pixel as the input,
Yeah.
the output would be the input for the neural network. Then you
Yeah.
take this
And you run it through
and
the
run
network.
it again.
Now, there's no magic here, and this was my point in the middle, and maybe I should have done this at the end. When we go from the pixel, the 2-dimensional point, to the high dimensional space, there's many answers, right? Obviously. The way that we do that is such that it's almost like you have a sheet that's fitting the points in the high dimensional space. And what you're doing is you're figuring out where you are on that sheet. So it's a highly constrained version. You can't go everywhere. Okay? So that's what you're doing. Okay, and then once you do that, you have this decision boundary map, and now you have a sort of a nice little profile, a constrained profile. Subject to your training data of where the class values. All right. Another awkward one. Well, this one's, I don't call it awkward. It's cool. I find it very cool. Do you guys know about precision and recall in terms of machine learning? Yes, we've got lots of, no, yes, maybe, okay, we've got a mix. Okay, so precision, I like to call, you better not be wrong. So I can get very, very high precision. What's your name? Parisa? Parisa. By going, that's Parisa. And then for everybody else's name, just not answer. Okay, that's high precision. Why is that high precision? True positives. I think there's only one Parisa in the room, right? Is there another one? I'd be embarrassed if there was. There isn't. So there's only one Parisa in the room. So we got 100% true positives. Okay. And false positives, we have 0. We haven't accused somebody of being Parisa when they. Okay. So precision is really important. Let's say you have some sort of really scary result, like somebody has a very bad disease. You want to make sure you have high precision because you don't want a lot of false positive. Okay. Recall is essentially we want to make sure we get all of the presets. So for that, I would go, are you preset, are you preset, are you preset, all through the group. Now, if there's a second or third preset, we would have high recall because we got all the presets and we didn't miss any of the presets. So with precision, we're scared about false positives. With recall, we're scared about false negatives. And this is often hidden in accuracy. So accuracy is just total questions and total correct responses. Okay. So we can look again at dimensionality reduction. So now we're using machine learning metric. And we're going to make a dimensionality reduction method around it. Okay. So in this particular case, we have a high dimensional input space. And we have a point in that high dimensional space I, and we have a hypersphere around it. And we have a set of points that are true neighbors. And we have a set of points outside of those that are not neighbors in the high dimensional space. Okay. And then by some method, which I'm not going to provide details just yet, we now have a 2-dimensional version. And if we have a green point that is within the circle of the dimensionality reduced point yi here, then it is a true positive. If you have a situation where the green point is outside the circle, then it is a false positive. And you can also have, it's a false negative. And then you can also have false positives, which are far away points that are within that circle. And you can optimize essentially these information retrieval functions around each of the individual points to compute a dimensionality reduced space. And now you can have control over precision and recall. So you could go 100% precision and you'll get diagrams like this. So the input is a sphere. At 100% precision, points nearby will be nearby in the high dimensional space. You're sure of that. Okay? You aren't going to falsely accuse people. But if it's far away, you can miss. So you can have these false negatives. So for example, these points here, which are very far away from these points down here, you've missed those. You're lower on recall. Likewise, you can do the opposite. You can do very, very, very high recall with low precision. And in this case, you take the sphere, it basically takes the sphere and smushes it. When you do that, you will not miss any of the neighbors along this border. But you will incur a bunch of problems in terms of precision, because stuff on the opposite side of the sphere gets pushed down. So I managed to start with dimensionality reduction, show how dimensionality reduction is related to graph drawing, and then start from machine learning and show how you can do dimensionality reduction with that. So we've gone both directions. Here we go. Okay. I haven't talked about users. I'm going to do that in a second. Do people want... Oh. I didn't realize I took I took a lot of time. Because I have a fair bit of slides here. Do people want a little bit of a break? Yeah.
I guess the coffee break will be 15 minutes. I think you should continue, then make a break, and then you could use a little bit later, time later on. Because you have 2 hours break over lunch. I think that is quite comfortable.
Okay.
So I would suggest to go for 50 minutes and have a proper break for that.
Okay. Maybe I don't rocket through this, but all right. So this is going to be based on a little bit of a presentation that I've given a couple of times this year. So the introduction is not there. So smart ML people, they like visualization. We already saw the Jeffrey Hinton paper, which starts with the word visualization. So some of them rely on dimensionality reduction. One important thing that you should know, and this is a little bit related to that division. So back in the 90s, you'd have visualization people talking about dimensionality reduction people talking about visualization. Often what happens now is because the fields are so large, there's a little bit of a divide. And I think part of the reason behind the Euroviz paper was to say we need to start looking at each other's papers again. But one of the things that distinguishes visualization and graph drawing people to some degree from machine learning people in terms of visualization is the user communities. So quite frequently, I would say the machine learning people are interested in model optimization for their visualizations. So a very particular audience, where visualization people would be interested in more diverse audiences. How do we speak to the general public? How do we speak to different user groups with different levels of expertise? This is where I think we have a really strong contribution to make. So governments and organizations, they want oversight of AI. Many governments and organizations have spoken about the need to understand decisions made by the AI. And one can view the machine learning as the engine and visualization as the windscreen. So insight is not for computers, insight is for humans, and oversight of AI is not for computers, oversight is for humans. So thus we necessarily have visualization, and visualization is a really important part of this so that broader audiences can understand what these things are doing. I think have you guys seen the data source yet? No? No? Oh my God. You haven't seen the data source? Okay, I'm gonna go through the data source stuff. So the data source is a little bit like Anscombe's quartet, but a little bit more ridiculous. Somebody added a computer to Anscombe's quartet. I didn't do it. Some guys at Autodesk. It's a very good example as to why you need visualization of things, as opposed to just tables of numbers and statistics. So here I'm going to go. All right. So I'm going to give you 5 statistics. Okay. Here are the 5 statistics. I'm going to have a variable X. I'm going to have a mean that's that. I'm going to have a variable Y. I'm going to have a mean that's that. I'm also going to set the standard deviations above. Okay, up to 4 significant digits. And then I'm going to set the correlation to negative 0.06. And that's what it's going to be. What can our data look like? What do you think? 1 plot? 2 plots? Well, it could be all of those. That has all of those statistics. So you could have no noise, you could have lines, you could have an X, you could have concentric circles, you could have clusters, you could have no clusters, you could have stars. Could be any of those. And it can be a dinosaur. So you might want to look at your data. A few years ago at this conference in 2018, somebody did the data source for graph drawings. So all 4 of those have the same number of vertices, edges, triangles, girth, and clusters. And they made a little bit of a tool where you can have a set of metrics, choose some subsets. And you can have very, very different graphs with the exact same metrics. So the moral of the story, make the Anscombe 1973, make both calculations and graph, both shorts should be studied. Each will contribute to understanding. And then Alberto Cairo, who said it a little bit more strongly, never trust summary statistics alone, always visualize your data. Even Alberto Cairo doesn't say throw out statistics. Okay? We do need statistics. You should probably also look at your data. Because for whatever statistics you choose, generally you're going to have wiggle room to have very, very different stories with the same statistics. Okay. So we have a little bit of motivation for graph drawings and other things for why we should look at these sorts of things. We looked at ways of visualizing ML models. I'm now going to talk a little bit about how to visualize COVID-19 disease models. Why? was very easy to talk to more general audiences during the pandemic. The main reason with general audiences is usually with data science concepts, it's very hard to get over the initial barrier. You know, you're talking about abstract things. You have an abstract thing now that has a very concrete reality. During the pandemic, if you talked about things like R number, a lot of people would understand what that meant, or they had an intuition about how that meant. So it was an opportunity to explore essentially data science with diverse audiences. And I'm thinking a lot of this stuff can happen with AI, but I haven't figured out how to do it yet. So before the pandemic, I was a graph drawing person, and I used to draw things like this, social networks. So in this particular case, we have tweets, and an edge is appearing if there's a mention of another Twitter account. And this is about rugby in the Guinness Pro 12. And we have a little bit of an idea of how these sort of co-mentions evolve over time. One of the contributions in the social media space that we did is if you look at old dynamic graph drawing algorithms, they typically function on time slices. So you choose an interval of regularly spaced time, you divide it into slices, you connect the similar vertex if it persists across slices with a line, and then within that slice you have a graph. And then you can optimize over the two things, drawing graph and inner time slice edges here. But Twitter's not structured that way. Okay? With Twitter, a particular communication happens down to the second, a particular co-mention happens down to the second, and it can be distributed very differently in the volume. You can have a lot of activity about a topic, and then very little activity above it. And so we came up with a three-dimensional algorithm that essentially draws these edges, which are surfaces, and nodes, which are polylines, in the space-time cube. Why do you want to do this? Well, both these high and low frequency features exist. So for example, you could have a situation where you have a topic and then, there's hardly any activity about it. Donald Trump said something, everything explodes, and there's a whole bunch of activity. In that case, you don't want a lot of time slices before Donald Trump says something, but you do want a lot later. That can't be done with regular time slices. Also, imposing these regular time slices, if there's no activity, imposes motion on the vertices because they just flop around with the repulsive forces. And also, if you don't like the set of time slices you selected, you need to select a new set, so might as well draw it without time slices. Social media is set up this way, so is contact tracing. Generally, people don't decide at 1 o'clock to meet up and then separate for an hour, right? It's spread out through the space-time cube. Okay. So this was my first contact with contact tracing. So this is a work done with Tatiana von Landesberger and one of her students, Tom Barbertall. He'll be here. He has an entry in the GD creative competition. We'll see exactly how we do. But this was work where he was studying infection control in hospitals. So we have an antibiotic resistant bacteria that can spread through infected catheters, but you don't constantly test the person within the hospital room. So you have a situation where you don't know where the transition happened between tests. So we came up with a visualization here to visualize the contacts. So you have a storyline here. So two of these lines are close if the two patients are in the same room and separated otherwise. And the infection control expert can map backwards to try and figure out where the infection came from through these graphics. Now, a little bit of a separate side story. I was writing this first draft of this paper in a hotel room in Japan in February of 2020. A little bit nervous about what was going on. Managed to get back safely, but then a month later, we entered the first lockdown. And when we entered the first lockdown in May, I was contacted by Min Chen, who put me in contact with some people at Glasgow, and they had a contact tracing model for simulating government policies. So you had a very large network that would be simulated contacts between individuals. So this is a temporal network, similar to the ones I was drawing with social media. So you have an edge with a specific time. And then what you do is you put COVID on top of this. Okay. And then you see where it spreads in the network. And then you can apply a different policy. And you can see if the spread was hindered by that policy. Okay. Now, at the same time, you need a method to model the progression of the disease within an individual. And this is a compartmental model. So in a compartmental model, this is essentially the states of the disease. Most people will start out as susceptible, and then they're exposed. That means they get exposed to the disease, and then they can go down two branches in terms of COVID. This is not true for all diseases, but in COVID it is. The first is the asymptomatic branch. So that means you go up to I. You don't actually feel COVID. You just walk around and spread it. With COVID-19, it's kind of hard to understand how many people are asymptomatic, but if you're younger, if you're a kid, you had a greater chance of being asymptomatic. My nephew, when the entire house was down and sick, was just running around being a vector, for example. So that's not so bad. It's bad for spreading the disease, but some people are. And then you have the symptomatic branch, which for 4 days you become pre-symptomatic, so you can walk around and that sort of stuff, not knowing you had symptoms. And then after that, you develop symptoms. And depending on the severity of the symptoms, you may need to go to hospital, etc. And within 2 days, we took our social media software. We produced the visualization. And our epidemiologist went, oh, I don't think this is the greatest visualization in the world. But they had nothing. And they were just so happy to see their data. And they actually did get something from this visualization. The main thing they got from this visualization is they were not expecting this many components. And the reason why in their model, they had a parameter for imported cases. So at the beginning of the pandemic, majority of cases were people on flights coming in. And by May, flights had basically stopped. So they had to actually turn down that parameter. And so the fact that there were so many components meant that they needed to turn down a parameter, this complex thing. Yep. Sorry? Oh, sorry. So in this case, these are people being infected. So here, I'll show you. So I showed you the compartmental model. That's the compartmental model. You have this temporal network right here. An edge appears and the disease could be transmitted along that edge or not. Okay, so you actually have people that are going through the compartmental model and people that are undergoing contacts. And that network is the people that are being infected.
So
from doing the things.
because they had also false negatives, we don't care about them.
So in this particular case, because this is simulated contacts, we know exactly who's getting infected, who's not. Now, in real contact tracing, we don't. And you can get false positives and true negatives. Here, we only have true. And we're looking at 100% simulated data. It's unrealistic, but in terms of modeling policies, it serves an advantage. Why? You know the conditions under which somebody exactly, and you can decide if the policy prevented it or not, right? So it is a simplification with an advantage. All right. And I guess this is where I take a break. Right? Okay. Of course, the other lectures are the ones that aren't back yet, so. I'll just point that out. Okay, we might as well pick up from where we left off. So we had this not so great visualization that basically showed the spread of COVID according to this simulated contact tracing. Okay. And it was really interesting dealing with these epidemiologists. We talked to one of them before this process started, and she didn't even know that visualization graph drawing was a thing. She didn't even know it existed as a field, let alone anything else. And when they saw this, they were like, wow, we can finally see our data. This is great. Personally, I don't think this is the best visualization, but I mentioned the number of components actually changed what they were doing in their simulator. So after this buy-in, we created a method. So you use their simulator to essentially do COVID on the disease, COVID without any restrictions, without any government restrictions. And then what you could do is you could apply certain government policies afterwards. So things like isolate 14 days or X minus Y. So isolate 14 days would be as soon as you have symptoms, you go away for 14 days. X minus Y is essentially you measure the duration that you've had symptoms, and then you go 14 minus the first day where the symptoms started. And that's your isolation period. So one's a little bit more lax. And what you can do is you can essentially compare the effectiveness of these policies on these trees. Now, this is a perfect forest of trees. Why? As rightly pointed out here, there's no false positives and there's no false negatives here. We know exactly where the disease went. The disease either spread or didn't because it's a simulation. And since we know those conditions at each of the nodes, we can decide whether or not under this policy, if the disease would have spread. Right? And then that's essentially what these bar graphs here are. We're comparing the left-handed policy with the right-handed policy. And where you see green, that's a prevented case. And then the other colors down there shows what state the individual was in when the disease spread. And you have a whole bunch of these trees. We use a method to cluster the trees, essentially based on some of their statistics. And this was a Euroviz 2022 best paper honorable mention. But this was for epidemiologists. Part of our idea with this project was not only to explain things to epidemiologists to help them, but to also explain things to the general public. And why was this so important for COVID? Well, think about the data science problem that we were facing there, right? You show some simulation, you say, therefore, you probably shouldn't go or leave your house so much. And then you could do this one of two ways. You could either go general public, trust the science, or you could say general public, this is how the science works. Play around with it if you'd like. Figure out, sort this stuff out of this and come to your own conclusions. I think version 2, even though at the end they could say, I still don't trust your science, at least with version 2, you've tried. Okay? So this is part of the reason why we were so interested in communicating to the general public. So we worked with essentially an organization called Technochems. And we explained to the general public and also to school children. So, and give them a little bit of an idea of what disease modeling and contact tracing modeling looks like. It's important in these sorts of visualizations and simulations, we don't need a super accurate model. We just need something that is understandable and close enough to the real technology. It just doesn't need to give the absolute precise number of cases. All right. This was delivered as part of a series of workshops in Wales, and I think it's still being delivered a bit. And at its height, it was seen by hundreds of students. It's one of my more used visualizations. All right, so we might as well give a little bit of a demo. Okay. So at the beginning, and they had a little bit of a workshop in the room. So people would stand in a room and they would touch each other's shoulder, and with the roll of a dice, you decide whether or not they would infect somebody else. I have a conjecture for the biz people in the audience. I think data physicalization is really important as a first step to abstract data visualization. I don't have any evidence of this yet. There's probably a PhD in there somewhere, so keep that in mind. My ideas may be different than yours. But anyways, so we did this physicalization, and then they repeated the same sort of thing on a graph, where we took the people, contracted them down to dots. You'd roll a dice and color in nodes on the graph. And then we gave them this tool, so we scaled up the number of people. As you can see, in the lower left corner, we have a very, very simple compartmental model. In these workshops, we were explaining zombie outbreaks. So it was a fictionalized scenario about zombie outbreaks, leading to one of my, so this was a Chi 2023 paper, and the first part of the title is From Asymptomatics to Zombies, Disease-Based Modeling for Children. Anyways. So you have a simple compartmental model down there. You can do things like compare R values. So these R values are not correct, but it's an idea to sort of give a little bit of an idea of the growth of exponents and how that's much. That these things are exponents. Okay. Yes. So in the actual classroom when they were doing it, it was, I believe, if they tried it if they rolled a 5 first, and these diseases basically push that faster than if it was odd numbers. So to give them a little bit of an idea of if your chances of getting infected is 50% versus 1 in 6. Then, yeah. And this is how we led into the Carnot discussion. One is higher than the other. Okay. And so you could try them. We had standard, and we used the language of the pandemic Delta, which had a Carnot of around 8. Delta plus policy. So we had a ability, and I'm going to show in the next visualization, to simulate what happens when people self-isolate. And then measles, which has an R naught of close to 16, to give a little bit of an idea of this. Okay, so let's go back to Delta. And we're going to go down to, where is it? Advanced. So in the advanced thing, it looks a little bit more realistic. So your people are starting at home, going to work, school, and going back. We model asymptomatics. And these asymptomatics won't realize they have the disease, so they will never self-isolate or anything like that. An interesting thing about this compartmental model, if you go all the way back to the compartmental model that we use in the expert system, it's not too dissimilar. So we're even able to explain this, what a compartmental model was, to a really high level of detail. Of course, we didn't talk about differential equations or anything like that, but the model was explained to a high level of detail, which is important. One of the things when we were talking to techno camps is the first thing we did was we got rid of a whole bunch of the parameters, and they immediately said, put them back in. So never underestimate school children, let's just put it that way. You can also do different policies. So if we go to policy here, you'll see people now will self-isolate, and whenever they show symptoms, they will self-isolate, but the tan colored ones, because they're asymptomatic, they don't know they have the disease, so they continue going on. With one of the sliders, you have a disobedience slider, so you can set disobedience to 100% and see what happens. Of course, the disease continues spreading. We captured a lot of qualitative data here. There's a fair bit of evidence from some of our things on the qualitative side that the students were actually understanding the disease well. We had one case of a student that tried to make the disease go forever. And so essentially what they did was they set the asymptomatic rate to 100%, and they turned off all of the policy. And that makes sense. And of course, some people were trying to kill the room faster. And we did report on that, and some of the reviewers were like, oh, it's like to do that. Okay. But based on these things, the fact that they were actually trying to compete with one another to get certain effects of the model, it indicates that they understood what was going on to a relatively high degree, which is great, because this is a real hardcore data science concept being understood by the general public. All right. I have a feeling, is it going to go all the way to the back? Yeah, I knew it was going to do that, because it does that. Okay. So as with all projects, I'm going to acknowledge some things. So thanks to the funders for all of their support. And Also, thanks to the larger project team for these projects. Okay. So this talk has been in 3 sections. I worried at the beginning that I was going too fast, and then I discovered halfway through that I did my standard thing and extended this thing to well over an hour and a half. So the first thing is, yes, when you get older and you give more presentations, the talks get longer. So GD and dimensionality reduction do have a strong connection, and they have a long-standing connection. And in the 90s, they were writing about this connection. But nowadays, because the machine learning field is gigantic, and dimensionality reduction is what they're interested in, mostly look at dimensionality reduction and rarely look back at GD. And we can say the same thing with ourselves. So we should probably look a little bit more at the dimensionality reduction literature as well. A lot of the algorithms are similar, and the one that I highlighted, the connection between Kamada-Kawai and MDS is very strong. Essentially, you're pretty much the same algorithm. You take shortest path versus high dimensional distance matrix, swap in, swap out, and you essentially have the same approach. All right. The other thing is MDS in particular, and a lot of these dimensionality reductions techniques, such as TCNE, can be used to not only visualize the data going into machine learning algorithms to see class separation, they can actually be used to visualize the machine learning algorithms themselves. And we do this by visualizing the neuron activation and treating that as a high dimensional space and reducing down there. And because I said before, if you do GD, you're kind of doing dimensionality reduction, you can contribute here too. So look for opportunities there. And then the final part is for functioning society. And I've said this a couple of times. People definitely need to be data literate. We've seen from the pandemic that sometimes people aren't. And they aren't visualization literate as well. In the next little while, we're going to run into a bigger problem, which I'm advocating, because people are going to need some level of model literacy. I think it's insufficient for the scientific community to go to the general public and say, this machine learning stuff, trust us. You don't need to understand anything, just trust us. On the other hand, I don't think they're going to have to be able to write their own models. But we're going to have to find some middle ground between those two extremes. And I think that's going to be one of the big challenges for the visualization community. And because of the connection between high dimensional data set visualization and graph drawing, one of the connections to the graph drawing community, one of those problems that we're going to need to solve as well. And so with that, I'm going to finally end my lecture. And we'll go on to a little bit of exercise. Okay, so I don't have a problem set. What I do have, you guys have literature here. I'm going to ask you to get into groups. Okay, and we have essentially 3 questions. You can do some literature reading around this topic. The first topic is dimensional reduction only. I included this one because the GD people know about graph drawing, right? Maybe it might be nice to look at the dimensionality reduction literature just to get your hands dirty with some of that. I have a survey, and this is on reliable visual analytics for dimensionality reduction. It's the GD2025 survey. You can use that as a starting point to go out. Likewise, you could directly look at the connections between graph drawing and dimensionality reduction. And I have that survey there from your visit this year, which you can use as a starting point. And the final one I don't have a survey on publicly accessible models. I have a bunch of papers from my own, which you can start from. But if you guys are more interested in HDI type topics, I would suggest you go and do a little bit of a look for publicly accessible models. So for the next little while, and I can come around and we can have discussions for about the next 40 minutes. Just get into small groups and start doing some searches on those topics. Does that make sense? You only have to do it on one of them. You can choose one of them. You don't need to do all three. Maybe you want to do all three, but you just need to choose one. Okay, I'll let you get started.